So shall we start? I don't see many people.
Uh, Good afternoon, everyone. So this is the last session. This is the last session. I think 14th session of this workshop, which will be taken by Dr. Gunjan Soni. Dr. Gunjan Soni is assistant professor in the Department of Mechanical Engineering, and he is also the convener of this workshop. I think he will be, I think, delivering on statistical measurement in mechanical other domains. So, Gunjan sir, welcome.
Yeah, thank you, sir. So I believe that every one of you have thoroughly enjoyed the sessions which were there before this, and this lecture of mine actually starts from where the instruments have done their work. They have done the measurement. Now the work starts where we want to know whether the measurements which have been done are reliable or not. We've taken the measurements from different sensors or through the use of various softwares. We've done the measurement, we recorded the data, but now we want to check the reliability of the data. So it brings all together another field, but this is the bridge lecture between the finding out whether the measurement system that has been used earlier is good enough or not, because in market there are a lot of sensors available, there are multiple softwares available which do the similar task. This all, if there's a wear and tear involved in the probes with which we are taking the measurement, there is a possibility that the measurement item that we have been using or the device which we have been using has become faulty over a period of time. So how do we ensure that a certain measurement system that we are using is good enough or not? It's a very wide field. I'll take some small cases in that, and it will just make you aware about how it has to be done, or what are the basics of if you're thinking about finding out the reliability of a measurement system. So my lecture is a very basic lecture, and at the end I'm also going to use a software called Minitab to facilitate the measurement system analysis. So, what is measurement system analysis? We can see that it's a set of techniques. So, we can see over here that it's not a one single methodology. There are multiple methodologies under the umbrella of measurement system analysis. We'll focus on one particular type of methodology. We'll see that. It is a set of techniques which allow us to answer the question, the basic question, if I use this gauge, or it could be an instrument, or it could be a software to measure how much I can trust the measurements I'm getting. So, how do I build the trust? Because if four different measurement systems are there, and if you take the same measurement with the four different measurement systems, it's quite possible that you may not get exactly same results. So how do I ensure my trust in that? So we have, for that we do measurement system analysis, and is based on a measurement error. So how do we check the measurement error? The traditional way of doing that is you take multiple measurements of similar item, or take so if I have to ensure a worker or an instrument is good or not, so I'll take multiple measurements from that instrument and find out average of that. Okay, that's the way the observations are taken in experiments, and then we do that. Or we take a single, that's what. So, thing to understand, it's not necessary that every time the measurement error may exist only in the device or in the software. It is also possible that it may be due to the worker or the appraiser. So, both the ways it has to be seen. It could be there in the appraiser. Error could be there with the technique which is being used to measure with the item. It is also possible that the problem may be with the device. So we can see over here, if even if we take different measurements using the same device, and if the measurements had to be identical, for example, let's say we are taking measure a 10 centimeter long item is there, and I'm taking measurements of that item. Or for example, let's say in this case, it's a very small dimension, which seem to be varying from 0.465 to 0.50. Now, although and this device which I'm using to measure this length, it's giving me different results with the frequency. Maybe I've taken 100 different observations, and if I make a histogram of those observations, it looks like this. So one thing that we can see that all the time the measurements are not going to be the same, but that is natural. Why it is natural? Because there is a random component, a random variable associated with measurements associated. There is a random variable associated with it. Now this random variable could be an error. Like we say, it's a random error. So also there's quite a possibility that error may be there because of the instrument. It is also quite possible that the error may be there because of the worker. So we can attribute it to three different things. Not necessarily there are many other as well, so we'll see that. But we see a lot of variation is existing. Now I need to examine this variation, whether this variation is because of the randomness, whether this variation is because of the external factors. If this variation is because of the randomness, I need not worry about it. But if variation is because of the other factors besides the randomness, I should be worried about it, because the it anything could be faulty over here. So I'll go ahead. So there's a term called bias of the system. So here you see, let's say this is the mean, and the blue line is indicating the frequency distribution. It some people might even see it as a normal distribution, uh, but then I'll not go into that. That's not part of this lecture over here. But you have to study about statistics if you want to go into details. But I'll try to be as brief and concise as possible over here. So let's say I've done many measurements, and they are following a certain normal distribution, or this bell-shaped blue curve. Okay. Now imagine we had measured a reference size and a standard is known. So we know what we are expecting. So we could compare the mean of the observations which we are getting over here, and this we compare this mean of the observations with the standard number which it should have been. So they mean to say over here, let's say I have a standard piece like a slip gauge, okay, with me. I know what is the thickness of this slip gauge because it's a standard piece. I've purchased it from the market, and using this standard piece, I want to know how is my measurement system performing with respect to this. So simply what I'm going to do is I'm going to do the measurement using my measurement system. And let's say I do 100 measurements, and for example, let's say this thickness of this slip gauge should have been 5 centimeters. And according to my 100 measurements, and I find out the average of that, the mean, it is coming out to be 4.7. So I call this difference as a bias. Okay. So that's what is explained over here. Now this bias will study about this bias. So reference value is 0.5. Basically, reference value means standard value. It should have been 0.5, but it is coming out to be, average is coming out to be 0.525. So there is a bias of 0.025 over here. Okay. Next, then how do we deal with this bias? Shall we, because this bias, there is a very, very bright chance, or very high probability that you are going to get bias. It is not natural to get exactly 5 value. So for that, we need to examine two things. The bias may change depending on two factors: linearity and stability. So linearity is change in bias over the operating range of the gauge. It is something like a gauge is designed like simply weighing machine. You consider a weighing machine. Now this weighing machine has range from 0 to 200 kg. Now, although this machine is designed for a maximum of 200 kg, but the linearity, the proportionality of the reading with the actual weight on the weighing machine may not be proportional, uh, let's say after 150 kg. Okay, so that's what it means over here, that there's a good possibility that linearity may this there's an increase in bias. The bias may start to increase if you increase the weight. So this weighing machine is generally made for people maybe weighing from 100 to 10 to let's say 120 kg. But although it is reading is maximum reading is around 200, but it may not show the proportionality with the weight if you operate it in a higher range. Similar things may be with the thermometers uh, and many other devices like voltmeters as well. So you can see some kind of non-linearity or deviation from linearity in such kind of measurements. Then you have stability, that is change in bias over time. So this is a different thing. You keep on using the instrument over and over again. What happens is that because of the mechanical components inside the system or straining of the system or the removal of the measure of the markings or the indicators, it may not show the same reading what it used to show even observation. So the bias may creep in as stability or instability over a period of time. So these are two forms of bias. So how do we examine these linearity and stability? So for example, you can see over here that here the bias at reference is 0, and so we can see over here that the bias may change. This is just an example of linearity, that your operating range is from 0.2 to 0.575. So the kind of bias which you may expect at a reference value of 0.25 may not be same as that at 0.25. Then this is stability, that is change in bias over a period of time, that as the time progresses, uh, your small blue line over here, the small blue line given over here, it is indicating increase in bias, right? So this is what is the meaning over here. Now there's a term called repeatability and reproducibility. So this is something quite interesting and important as well. So bias is based on location of the mean of the distribution. So what do we see that over here the variation is existing. Now this variation needs to be studied. So the best way of studying the variation is through standard deviation and variance. But it's not easy to uh, measure it first. If you are able to measure it, then the classification of that, because this variation may be simply because of the natural randomness which is there in that. See, if I ask you, if I give you a 10 centimeter line, I know this is a 10 centimeter line because I've made it using a standard, very standard object. And I give you 10 different scales to measure it. I'm taking a very crude example. Every time it's not, and I give it to 20 different people. It's not, and I don't tell them this is a 10 centimeter line. it is quite possible that all these 20 people may come out with different readings, not varying much, but still variation may exist in that. That may be because of simple randomness which is there in the system. Now this random variable, this name itself random, is actually a misnomer. Random means that it follows a certain pattern, but in a given range, it can take any value in that pattern. It will follow a pattern, but there is a probability associated with that particular number which this variable can take in pattern. So that's what it means over here, the random number. This random number is existing everywhere. It's simply the natural variation which exists in the nature or the universe. And human beings or the measurements are not devoid of it. So, but at times, this variation may not be random as well. For example, you put an untrained worker on the job. There's a good possibility that variation will be there, and the random variation will also be there. But the component of the variation which is coming because of this operator, because of the unskilled nature of this operator, this variation is very high than the random variation. Getting it? Similarly, if you are having a machine, a measurement device, which is having problems like loose screws or worn out parts which are inside the measurement device, there's a good possibility that it will give you a lot of variation. And this variation may be not only because of the randomness, but maybe because of the machine as well. So when one person uses the gauge, we get variation. This variation is inherent in the gauge. That is, we term this as repeatability. That means if one single person is using the same gauge, same measurement device again and again, and the variation which is coming over here is termed as repeatability. So ideally, if only one person is using it, so the and taking the same observation again and again, variation should not be there. If the variation is there, you may attribute it to the machine. So any the error or you can say the variation which is coming in the measurements because of the gauge or the measurement system is termed as repeatability. While if we have more than one person using the gauge, so if many people are using the same measurement device, then there may be a variation which we term it as reproducibility. So the thumb rule could be repeatability represents the variation because of the machine. Reproducibility represents variation because of the human factors or the worker. So this diagram is indicating that the variation error because of repeatability and reproducibility. One is because of the machine and another is because of the worker. Then let's understand what are the possible sources of process variation. Now, in a given process, in an observed, there could be an observed process variation. Observed process variation is very simple. Let's say I'm producing a cylindrical part, and this cylindrical part is exhibiting some variation. Like ideally, I am trying to make a 50 centimeter diameter, 50 centimeter or 5 centimeter diameter. But then the observations that I'm getting are like 4.9, 4.8, 4.6, 5.1, 5.2. So there is a variation. So we say it is an observed process variation. I can find out the standard deviation by taking out reading by taking reading of all the observations that you do. Then this observed process variation could be because of two things. it could be because of actual process variation, or it could be because of the measurement variation. So actual process variation means that the machine which is producing it, the machine with which we are making the part cylindrical, that is the lathe, there is a variation existing in the machine, or or the person who's producing it, right? So not the worker who is doing the measurement, but the worker who's producing it. Okay, so he's also part of the actual process variation. So the machine which is there is a part of actual process variation. Now this actual process variation could be of three types: long-term process variation, short-term process variation, and variation within the sample. So long-term process variation means that the machine is worn out, the tools of the machine are worn out, and they need replacement. And these, so it is generally expensive. Short-term process variation could be because of some special causes like fluctuation in the voltage, or uh, one day the worker was not there, so some other worker was deployed in place of him to produce the part. So that could be part of your short-term process variation. Then you have variation within the sample, which we attribute as a random variation, which is generally random, and you just really can't put a name on it. Either it is because of the process variation, or is it because of the measurement variation. So that's why variation within the sample is part of both actual process variation as well as the measurement variation. Then you have variation due to gauge and variation due to operators. So variation due to gauge can further be classified as repeatability. Variation due to operators, we are already saying it is because it is the measure of the variation due to operators is reproducibility. So repeatability, calibration, stability, and linearity, all these are attributed to the variation due to gauge. So repeatability means there's a problem with the machine measurement unit itself. So the repeatability is suffering. The calibration is basically, I hope all of you know what is the meaning of calibration. So incorrectly calibrated measurement instrument will lead to some variation. So it is again we are attributing it that to the variation due to gauge. Then you have stability problem and the linearity problem, which we have already discussed. So now we know that what all different types of variation could be there.
Hello, hello, sir.
Yeah.
Sir, can you please switch to the full screen mode? It's looking a bit odd, like
Okay.
a small screen.
Is it fine now?
Yes, sir.
Okay. So here we see, I'll again repeat once. Observed process variation could be classified into actual process variation and the measurement variation. Actual process variation could be because of long-term process variation. The machine has worn out, it can't be improved anymore. So variation is coming with that. Then you have short-term process variation, which is because of some special causes, but eventually they affect the process. And variation within the sample is the random variation, which is very natural and exists in the nature. While then in the measurement variation, we have other two things like variation due to gauge and variation due to operators. Variation coming due to operators here is representing reproducibility, and then you have repeatability, calibration, stability, and linearity as the component. It has been found out that you can take care of linearity, you can ensure linearity by operating the instrument in a given range. You can take care of stability by regular maintenance. You can take care of calibration again by regular maintenance and making sure it is calibrated properly periodically. But then there is the error, that is repeatability, which is again a nature of the gauge. It's like 10 different parts together, variation in one part, variation in another part, variation in the third part, and the 10th part. Together, they form a composite error, which is a repeatability. So this repeatability is something which is not easy to handle. So it has been taken separately. Now, considering and assuming that stability, linearity, and calibration has been taken care for, we calculate sigma square is the variance of the observed process. So observed. So as far as the measurement system is concerned, we are only worried about sigma square measurement system. That is variance of the measurement system. So variance of the measurement system is largely because of the operators or because of the measurement system itself. So we say variance of the measurement system is largely attributed by repeatability and reproducibility. Now we need to do some measurements to check what is the contribution of repeatability and reproducibility in the complete variation which is existing in the system. So this again is indicating that so repeatability and reproducibility together they form a study called gauge R&R study, that is gauge repeatability and reproducibility study. It is a very important component in industry when they are sending an instrument to the market. So how does it look like? So let's say this is the variation because of the measurement system or the gauge variation. This dotted line is indicating the actual process variation, and the observed process variation would be a composite of these two, so which is much higher than individually taken. So there are two different types of gauge R&R studies which are generally used. First is comparison with standards, and the second one is gauge R&R cross. There are some many variants of gauge R&R cross, gauge R&R, but we are going to be focusing on only R&R cross, which is most generically used. Now, before we go ahead, we need to know it's not always possible to have standards. At times, it is possible that you have standards to gauge your measurement system, and at times you don't have standards to gauge your measurement system. So we are going to see both. We're going to see comparison with standards, and we are going to see when the standard values are not available. So when the comparison with the standard is concerned, let's say n is the number of units with pre-inspected standard values available. So it's like you all of you must have seen retailers are keeping 1 kg, 2 kg, 500 grams weights with them, right? And but we don't know whether they are correct or not. So you consider it that sort of a situation. So n is the number of units with pre-inspected standard values available, and n is the number of appraisers that can be assigned to perform tasks. And there are three things: n, m, and r over here. So n is the number of units with pre-inspected standard values. So some standard like 1 kg standard measurement weights are there with me. I know 1 kg. Now I can other weights and check whether those weights are of 1 kg or not. So it means n. M is the number of appraisers can be assigned to perform test. So how many? So what we are going to do? There should be no biasness in that. So we are using multiple appraisers or workers to do the measure inspection. And R is the current number of runs at any given time in the method. So it is very important that we do it multiple times. So we call it runs. Okay. So some terminology associated with this. Standard unit, any of the n units with the standard values available. Absolute error is absolute value of the measurement errors for a given test run. It's just the difference between the observed value and the actual value. And EEA is estimates error of the expected absolute errors. Then you have measurement system capability, which is MSA is equal to 6 into EAE. What is EEAE? The is estimated expected absolute errors. So actually these terms like estimate and expected, these are all in probabilistic terms. We don't have that much time, so we can discuss all of these things, but these are some of the formulas which are used. Then whether the gauge is capable or not, so I'm again repeating, we are doing it for the situation in which the standards are available with us. So gauge is capable or not. If measurement system capability MSA is less than D, D is something that we want to know. Like if some weight is there, if I have if I want to find out 10 kg weight as a standard, am I okay if there is an error of 0.5 kg? So D is that deviation from the actual value, permissible deviation from the actual value. So if measurement system capability is less than D, where D is user defined, maximum tolerable difference from standard value thus would be 6 into EEAE. If it is lesser than, if 6 into EEAE is lesser than D, we say the gauge is capable. So these are all empirically driven formulas. So the example is somewhat like this. There are two 12-pound dumbbells to determine whether the following measurement standard operating procedure is gauge capable of telling apart differences of 5 pounds. Simply means that I have 2-pound dumbbells and I want to find out whether the gauge is capable to tell apart differences of 5 pounds. So although it is very unrealistic situation, because no one would be comfortable with a difference of 5 pounds, but for simplicity it has been taken. So the standard operating procedure, so actually standard operating procedure is also part of your measurement system analysis, because this is a system. The system includes the machines and the procedures. So put Taylor metro scale has been used over here on a flat surface. We adjust dial to set reading to 0. We place items on the scale and record the weight, rounding to the nearest pound. So what are we doing over here? We can measure 12 pounds. We have two different units available with us, 12 pounds unit, and if we combine the two together, we have 24 pounds. So we can measure 12 pounds and we can measure 24 pounds. So this kind of randomized table is very important, where we do multiple runs, like 20 different observations are taken and 3 different people are, although here only one worker has been taken, but in the next study we will see much more realistic scenario. So standard units are there, standard like 3 units have been assigned over here. The third unit indicates that we are measuring 24 pounds, and 1 and 2 represent we are measuring 12 pounds. So worker 1, he'll pick the dumbbells together and measure the value which is coming out to be 22. Then he'll again do the measurement and will pick one dumbbell, the value is coming to be 12. So the scale, the Taylor metro scale is being tested over here. At times, Taylor metro scale is indicating an error of 2. At times, it is indicating an error of 0. So it is, if you look at it, the errors which are being shown over here are the absolute errors, and they are indicating variation. Okay, so Taylor metro scale under investigation over here. So the next step is that we calculate few things like EEA, which is basically summation of absolute errors, and we find out average of that. That's coming out to be 1.55. Then next, what we do is we find out triple EAE, which is 2 is your actual observation minus the average, that TEAE. So we find out divided by root 20 is the number of observations, and that's coming out to be 0.135. And the ratio is very much greater than 5. Uh, so we can expect that absolute errors we write it as 1.55 plus minus 0.135. So this is representing the variation 1.55 plus minus 0.135. So this is representing the variation from the mean. Now we want to know whether this is gauge capable or not. This this system, the measurement system analysis we've done, and we want to know that this this scale, Taylor Metro scale, which we are using, is usable or not. So we multiply 6 with 1.55, and the thumb rule was that it should be lesser than D. So D was coming out to be 5, not coming out, it was specified as 5 pounds. So can it tell the difference of 5 pounds? So it is 9.3 and greater than 5 pounds. So we say it is the gauge is not capable. Getting it? So although we purchased the gauge and did everything, but eventually found out that it's not good enough for the accuracy that I require. Now we go to the next part where the standards are not available with me. I'll not go through all these steps. You can these slides will be shared with you. I'll go to the study. Now this is the study. I'll show you the exact one. Yeah. So a weld engineer is analyzing the ability of two computer software programs. So there are two different software programs which are being used to do same type of measurement. Of course, these software programs would be having some machine vision based camera or some sensors would be there taking these observations. So we want to know this combination of software and the sensors, considering that the same sensor is used for taking the observation, but the input from sensor is going to two different software. So we want to see whether these two softwares are doing the same thing or not, or is there a variation existing between the two softwares. You can assume these softwares to be like appraisers or the workers. It is also very necessary that I take not only one part reading, I take readings from different parts, like different locations. So a weld engineer is analyzing the ability of two computer software programs to measure consistently the undercut weld cross sections. So welding cross sections are there. So these two softwares are analyzing them. So the values of the undercut weld cross sections are given over here. Now, how this study has been designed is there are 5 different places where the observation will be taken. It will be taken by 2 different softwares, and at every location or every unit, we are defining it as unit. That 5 different locations of welding, and each location is called as a unit. So appraiser means software. So every software is going to take a reading at each unit, and there'll be 3 different times, like 5 different locations, at each location 3 times by each software. So that makes it 30 different readings. So I write it. The thing is, there should be no biasness in this. So in order to remove the biasness, we have to randomize this table. There are many ways of doing the randomization. You can use any statistical software or Excel to do the randomization in every programming language, like or any software like MATLAB or R or Python. You have the commands for generating random numbers. You can do that. Once you're done with that, in YIK you're going to put your values, the observed values. So I'll substitute my observed values all over here, and I am going to do several calculations. Although this is not a class lecture like normal, otherwise in the class I'm going to ask everyone to solve it, but then we're not doing any class over here. So I'm just going to skip to the formulas, what formulas are used over here, and what kind of results come. Then we'll try to solve the same problem using a software. So we get this kind of table. Now here you see the superscripts are indicating the trial number. 1 to 30 would be there. It's like this is 29. This is the 30th observation, like this. So there are several things which needs to be calculated. Y average range, range of the parts, range inspected, then repeatability and reproducibility. All these things are calculated. And how they are calculated, these are the formulas which are used over here. We calculate repeatability, we calculate reproducibility, and it's coming out to be 0.017. Repeatability, reproducibility is coming out to be 0, which is basically related with the appraiser. And R&R is coming out to be 0.017. Part-to-part variation. Part-to-part variation indicates the randomness of the error, which can't be attributed to anything. So it's coming out to be 23.2. Now this 23.2, there are some guidelines that if your percentage R&R falls between 10 to 30%, it is not considered to be a very good percentage in terms of the error. If the higher the percentage R&R, the worse the system is. You don't want it to be high. You want it to be as less as possible because it is indicating variation. So you don't want too much variation because of the measurement system. Okay, so that's how we do that. Now you can see over here. I'll talk about this output when we solve it in Minitab. So I'm showing you an output of Minitab software. You can see that I have fed all the values over here. So it is not this software Minitab looks like a lot like Excel, but it is largely used for quality control in industry, and it's a statistical software. But it gives the capability of doing the measurement system analysis. So let's say all the dimensions are fed over here as 30 observations.
Sir, the software is not visible, sir.
Okay. Just a second. I have to. I shared only PPT. That's why. I'll start. I'm stopping to share. I'm starting again then. Share. I'm sharing the screen now. Okay. Is it visible now?
Yes, sir.
Yeah.
Excel file.
So we can see over here that these are the dimensions which I have fed over here. It looks largely like an Excel only, but it is not Excel. So this Minitab is mostly used in industry, largely used in industry by quality engineers, and or if you are conducting any experiments in engineering experiments, there you can use it. Design of experiments can very well be done in this. I'll just show you some capabilities like analysis of variance you can do, regression, control charts you can make, quality tools, many things like reliability analysis can be done over here. This multivariate, others, different type of statistics, time series. So it has very large capabilities, very large plethora of capabilities. But then let's say we are limiting our discussion here to only measurement system analysis. So I've fed all the values over here, and these are 30 different observations. I'm going to run it like I ran it. The results which I get, I'll just show you how we do this thing. So gauge study, and there are different types of gauge study: nested, expanded, crossed. But since we are doing only cross study over here, cross means that both both the appraisers are going to do measurement at both all the 5 locations, and the locations are not splitted between the two. That's what it means. So we do this gauge RNR cross. I have part number are in the part column, operators are in the appraiser column, and the measurement data is in the dimension. Method of analysis: ANOVA and X bar. Actually, for the people who don't know about these things, it's not good if I go into detail of ANOVA and X bar, because for that a different course is required altogether, a course on statistics. So I would not go into the statistical details of it, but I'm just going to show you through figures that what is the meaning of this. How do we visualize this gauge R&R? Okay. So we get this kind of these kind of figures over here. So let's try to understand these figures. Although this is for ANOVA, ANOVA basically measures whether there is a difference between the two operators or not. Okay, so the means which you are getting are same in case of A and B or not. Okay, so gauge R and R, you see over here components of variation. Gauge R and R, this is indicating this brown part is contribution and the green part is study variance. The contribution in the overall variation, and green part is study variation is generally larger than the contribution, individual contribution. Individual contribution in the variation, which is because of the measurement system. Okay, and study variation is the total variation, you can say. Right now I can just be crude about it. So we can see over here repeatability and reproducibility. Reproducibility is not exactly 0, it is approximately very small as compared to repeatability. So reproducibility indicates appraiser and repeatability indicates the measurement instrument. So the variation which is there because of the measurement instrument is slightly larger, while the variation which is coming because of the two different software, it is not much. So you can assume over here the softwares are working on similar platforms, the algorithms which are there behind these software, they are giving you more or less similar results. And part to part means this is the majority of variation is because of the randomness and not because of the measurement system. The second thing is this variation across the samples. If we compare for appraiser A and appraiser B, leaving one point here, this point, sample number 1, appraiser 1 is giving a very different value, very different range for sample 1 as compared to that of A. This one thing we can see. Remaining all are okay, not that great difference. Then you have X bar chart by appraiser. So any point which is falling outside the red line indicate, like here we have 1, 2, 3, 4. Out of 5 points, 4 points are outside the red lines. It indicates that this variation is not a characteristic of the measurement system, but it is because of certain special causes. So one thing we can, it is expected that these points should be outside. If these points had these points been inside, it would say that there's a good amount of variation existing inherently in the software A, or similarly in the software B. So in software B as well, 4 points are falling outside the control limits. The red lines are called the control limits. So in both the cases, the points are falling outside largely, except 1 point here and 1 point that's also on the boundary. So most of the points. So whatever the variation is coming because of repeatability and because of the measurement system of A and B, they are all because of some other reasons and not because of the measurement system as such. If these all points were inside the red lines, then you would have seen these skyscrapers would be higher. Then dimension by part. So anyway, it just showed that how the variation is for different parts, 5 different readings. So readings are pretty close except for the fourth part. We can see that. And this is the box plot for A and B. B is showing higher variation as compared to A, which is also indicative of the repeatability. So B is showing higher variation. B is showing higher variation than A. And here is the appraiser interaction. Appraiser interaction means that although these are software, they don't talk to each other. But assume if they were workers. If these two workers had been talking to each other and their curves were like this, we could see that there is a biasness. Like one worker is doing measurement and this worker is telling others, okay, this is the measurement, write this value without actually measuring it. So that it tells the appraiser interaction. It is expected that these two lines should not be very much close to each other or identical to each other. If they are very identical to each other, it indicates there is a possibility of bias. It is not natural for A and B to show exactly same curves. Okay, so these are some of the outputs we understand. Besides this, if we look at some of the numerical values here, I won't go into all, but let's say this last table is somewhat we can focus on. It tells over here that part to part variation is 96.97%. That is the variation which is attributed by measurement system. Of that variation, 96.97% is because of the randomness. Okay, and then you have total gauge R&R of study variance is 24.41. Now let's go back to the slides. So some guidelines given regarding that. So if it is if this is coming out to be less than 10%, if study variance comes out to be lesser than 10% of total gauge R&R, it is acceptable. If it is coming between 10 to 30%, it is acceptable depending on the application cost and factors. It depends on the criticality also. If you are doing measurements of nuts and bolts, which are used for not very precision works, we can say if I try to increase precision, I'll have to spend a lot of money. So I'm okay with 10 to 30%. But if you're talking about aerospace or satellite launch vehicles or satellites, these are very expensive decisions. So you may not want to take any risk in that. So probably you may want to, if you're not getting measurement system capability less than 10%, you may want to buy a new setup altogether. While if you're getting more than 30% study variance, then we can say that it should be improved. So if you look at these figures over here, what is the contribution of each type of error? It can all be found out from different these things values over here. So these are some of the things for today. I have given you some exposure that once you're done with the measurement, once you're done with the sensing, once you are done with uh, all the thing, you may think that okay, it's over now. Actually, further investigation is required, especially when you are establishing the systems or regular maintenance, when you are doing the regular maintenance of the measurement system. So now you will be having this feedback session, which Parikshit sir will be organizing. So we stop this lecture over here. We'll take a 5-minute break. Meanwhile, don't go offline. Please be here, and soon we'll be starting with the validatory session. So I hope you would have enjoyed all the sessions which were there earlier, and many new things you would have learned regarding LabVIEW and the measurements, things like IoT and Industry 4.0 and all. So I think you might have received feedback form. Did you receive the feedback form yet? Yeah, anyone?
Yes, sir.
Okay. So please fill that feedback form. Meanwhile, we'll be resuming with this validatory session soon.